Molecular orbital theory?
Yeah.
There's not much to it, but you do have to have a different mindset for thinking about things. Because in this case, there are no more atomic orbitals. And you might ask, well, what does he mean by atomic orbitals? An s orbital is an atomic orbital. An sp orbital is a hybrid atomic orbital. And the reason they're called atomic orbitals is because they originate from a single atom and kind of go out, right?
Mm-hmm.
Okay, so those are atomic orbitals. Molecular orbital theory is a whole nother idea. And the idea is this, that instead of treating where the electrons are on a molecule based on each individual atom one at a time, let's think about the whole molecule as one unit and decide how the electrons are spread out over the whole molecule.
Right.
And so you have these things called molecular orbitals. Now, where molecular orbitals and hybrid orbitals overlap is that hybrid orbitals are made out of specific atomic orbitals like an S and a P, or an S, a P, and a P, right?
Mm-hmm.
Molecular orbitals, the baby molecular orbital that we're going to study, the idea is that you take one orbital from one atom and one orbital from another atom, and you combine those into two molecular orbitals. And the molecular orbitals cover the whole molecule. Now, for us, the baby part of this is that we're only going to do very simple molecules and ions that only have two atoms.
Yeah.
And we're really only going to do it for up through period 2 and nothing more. So nothing in period 3, nothing in period 4, 5, 6, 7, 8, anything like that, just period 1 and 2.
Okay.
And so there are some things that you need to know about molecular orbital theory. So I'm going to do a new share here. And this is a list of things that you need to know about molecular orbital theory. Okay, so you can hopefully see my paper here.
Yeah.
I'm going to zoom out a bit so I can show you a bit. So whenever I think about the theory, I always draw a very simple molecular orbital diagram. So this is the simplest molecular orbital diagram you can have. So imagine you have two hydrogen atoms. And these are your two hydrogen atoms. So this is, in a sense, an orbital box diagram, correct?
Mm-hmm.
For hydrogen?
Yeah.
Okay. And so here's one of my hydrogen atoms. And here's the other hydrogen atom. So here's the orbital box diagram, and here's like a picture of the 1s orbitals with their electrons in them.
Okay.
Okay. So these are AOs. Now, what do you think AO stands for in this case?
Anti.
Pardon me?
Is it the anti-bonding ones?
Nope, stands for atomic orbital.
Oh, okay.
Okay. So it turns out that when you have two atomic orbitals, they can make two molecular orbitals. If you had 3 atomic orbitals, you could make 3 molecular orbitals. If you had 4 atomic orbitals, you could make 4 molecular orbitals. So we're going to make 2 molecular orbitals out of this. When you make the molecular orbitals, you make one bonding molecular orbital and one anti-bonding molecular orbital. So here, I'm going to make a molecular orbital between these two, and it is going to be a bonding MO. And here, this is going to be the anti-bonding molecular orbital. So here, I'm going to call this MO. What's that stand for?
molecular orbital.
Excellent. And here, this one's is going to be MO star. And the star stands for anti-bonding.
Okay, yeah.
Okay, so this is a bonding MO and this is an anti-bonding MO. Now, what do they look like here? Well, here, I'm going to draw the two nuclei here. This is what your bonding MO looks like. Okay? So that means that we can put, because it's an orbital, and we treat it kind of like, we treat them with Hund's rule and the Pauli exclusion principle. So what that means is we can only put 2 electrons in there because of, the opposite spin and individual unique set of quantum numbers. So you can only put 2 electrons in here and that's it. Okay. And here's what the anti-bonding looks like. So here's the same 2 nuclei. And this is what I draw for the anti-bonding molecular orbital. And what you need to know about this is right here, there's a node. So what is a node? You should recall that even though we didn't talk about nodal planes or anything like that, a node is a place where you can't find the electrons. Okay. So here you can see that if you put electrons here, they're not going to make a bond. And actually, if you had an electron here and an electron here, they'd kind of repel one another, right?
Yeah.
So this is your anti-bonding MO here. And this is what it looks like in a diagram.
Okay.
And this is what it looks like over here. Now, if this were H2 and we wanted to look at bonding in H2, what we would do here for the molecular orbital diagram is we'd take these 2 electrons and we'd put them into the MOs. And again, you'd follow Hund's rule, which says, put them in the most stable orbital first. Now, we don't call this Hund's rule. We just say, this is the rule for putting them into the MOs, put them in the most stable first. So there's the first one. And how do you think the second one goes?
Up.
Down.
Oh, I meant.
So
okay.
even though they're both up, as individual atoms, yeah, we have them both up because that's standard procedure. But when you're talking about making a bond, you have one up, one down.
I thought you were moving on to the next one.
Oh no. So this is the orbital box diagram for an MO. Now over here, what kind of a bond is this? Well, do you see how the electrons here are really centered between the 2 nuclei? And you remember for valence bond theory, we had things called sigma bonds and pi bonds. So this is a pi bond or sigma bond, I'm sorry, because the bulk of the overlap is between the 2 nuclei, directly between them.
Right.
And because they're made out of 1s's, it's a sigma 1s.
Okay.
So here, I'm going to write that here, sigma 1s. And so what do we call this one where still, we're looking at the electron density being on the same line as the 2 nuclei? Well, this is called a sigma 1s, but star because it's an anti-bonding.
Right.
Okay, so this brings about principles of MO theory. So there's 4 principles that we talk about. So the best MOs come from AOs of similar energy. So what am I talking about here? 1s and 1s, not a 1s and a 2s, a 1s from one atom and a 1s from the other atom. Not a 1s and a 2p. Not even a 2s from one atom and a 2p from another atom. I mean, they're both in the second period, right? But no. Second period's not enough. You want them from the same period and the same subshell. And Furthermore, you want them from the same orientation. So you would not do a 2px and a 2py. You wouldn't do that.
Okay.
You do a 2px and a 2px, a 2py and a 2py, and make MOs out of that. But you would not do it out of a px and a py. Okay, so the best MOs come from AOs of similar energy. For 2 AOs, you get 2 MOs. One more stable bonding MO and one less stable anti-bonding MO. And here you can see I put the little star there so you know we're talking about an anti-bonding. And here you place electrons in the MOs in the more stable MOs first. And actually, now that I think about it, I combined 2 of the principles, but that's all right. Place the electrons in MOs, in the more stable MOs first, and if the MOs are equally stable, one per MO before pairing. And really, I'm going to put a little dot here because these are like 2 different principles. You get 2 AOs for 2 MOs, and here you get a more stable bonding MO and one less stable bonding MO. This one here, the one more stable bonding MO and one less stable anti-bonding MO is not always strictly true, but that's what we're going to write. So the reason I drew this very simple MO diagram here is because I can see all of these ideas right here. So first, best MOs come from AOs of similar energy. Can you see that these AOs are of similar energy?
Yep.
Can you see that I have 2 AOs and I get 2 MOs?
Yeah.
Can you see that I get a bonding MO and an anti-bonding MO? Can you also see that I'm placing them in the more stable MO first?
Yeah.
So drawing this is a reminder to me of all of these principles. And that way I don't have to memorize the principles on their own without knowing what they mean. So these go hand in hand. Are you with me?
Yep.
Okay. Now with these, when you draw these bonding and anti-bonding MOs, what you can also do here is you can draw these like greater than or less than signs up here.
It looks like ears. And then a pig.
And you can see that you've just drawn a pig.
Did you do that? Like, did you know that was going to happen?
What's that?
Have you drawn this so many times that you knew this was going to happen?
Well, you know, the first time I drew it, I thought, you know, damn, that looks like a pig. I just put it up on the board, and I think that can actually help you to remember what it looks like, right?
Yeah, that's funny.
So, I mean, I guess you could have, what else? Well, with a nose like that, it's got to be like a pig or a boar or something like that, right?
Yeah.
That's not really a dog. The dog's nose is more squarish.
Oh, okay.
Okay. Now that's the very simple MO. Let's look at a little more of the MO. So do you remember that this is the 2px? It looks like this, right?
Yeah.
And what I'm going to do here is I'm going to get a new piece of paper. And do you see what I did here where I took the orbital and I drew the MOs?
Yeah.
Well, I'm going to do that for the 2px, but I'm also going to do it for the 2ps. So here's a 2ps, or excuse me, a 2s, not a 2ps. And here's a 2s. So what are the, and these are AOs, right? So what are the MOs going to look like for a 2s? They're going to look like this. That's your sigma 2s, and it's going to look like this. Sigma star 2s. So does this look a lot like the 1s's? They do. But if we wanted to draw these out, we would do this. So I'm going to make these boxes. And we know these boxes on the outside are AOs, right? And these boxes on the inside are MOs.
Yeah.
Now, if I wanted to add this to this, it would look like this. So what I'm trying to show you is that these are more stable and these are less stable. So just like we would do for an electron configuration, those electrons in the first MO shell are more stable than those in the second MO shell.
Okay.
Okay? Now let's take a look at what happens when we do a 2px and a 2px. So here's a 2px, looks like this, and there's the nucleus. And here's another 2px. So what do the MOs here look like? Well, they actually look like this. We would combine these two together and we'd get this. And this is a sigma 2p bonding MO. And the anti-bonding MO would look like this. And here is your node. And this is a sigma 2p star. So you can see that the balance of the electrons are directly between the two nuclei or on line with the two nuclei. Okay,
Yeah.
so here's a 2p and a 2p star. So we good on that one?
Yeah.
So what would happen if you had a 2p y? A 2py looks like this. Okay, so here's the two nuclei. And when you make a bonding MO out of this, it looks like this. It looks like a sandwich with 2 olives in the middle of it. Now, are the electrons directly between the 2 nuclei? Or are they above and below the 2 nuclei?
Above and below.
Right. So what did we call that kind of bond where the electrons ended up above and below the nuclei when we used valence bond theory?
Pi.
So this is a pi 2p-MO.
So is that a double bond?
This is a pi bond.
Would it be a double bond?
Yeah, we would refer to it as a double bond, but that's not relevant anymore. It's a pi bond. Because there are some molecules you could use MO theory with, and you could get no sigma bonds and only pi bonds. So we don't really want to confuse the topic by saying, is that a double bond? That's not relevant anymore. It's a pi bond.
Okay.
And here's what the anti-bonding MO would look like. Here's your node. And here are the bulk of the electrons directly between the 2 nuclei or on line with the nuclei? And the answer is no. So this is a pi 2p star.
How does the Y orientation end up like that?
Because when you're making the MOs, these guys are side to side, whereas the X's are head to head.
On the same plane.
Yeah, the X's, because we're talking about the X's. Do you see how when they make their MOs, they're doing a head to head? You're basically taking this and matching it with that by pushing them together.
Okay.
So that's a sigma bond. Whereas
Overlap.
this one, it's side to side. So there's 2 types of, in valence bond even, there's 2 types of bonding. There's the head to head, like you could have a SP with an SP3 head to head, that's a sigma bond.
Yeah.
But whenever you had a pi bond, it was 2 things coming side to side. And here it's the same thing, but it just so happens that the 2px's, when they come together, they do a head to head, not a side to side.
Okay.
So if we take a look at that in the grand scheme of things, can you see how these 2 are side to side? If these 2 atoms come together and make MOs, these 2 are side to side, and these 2 are head to head. So when these 2 are head to head and they make MOs, you're going to get a sigma and a sigma star. These 2 Y's side to side, you're going to get a pi and a pi star. And here on this Z axis, when these 2 come together side to side, what are you going to get?
Pi.
Pi and a
Pi star.
pi star. Okay. So how do these all look together when you want to put them together? And this is where you're going to have to remember this, because there's 2 different ways that they all come together. So I'm going to show them to you in your book, and then we're going to draw them, okay?
Okay. Will we have time to do problems at the end of the chapter, you think?
Probably a little bit of time, yeah. Okay. So do you see this right here? Energy level diagram for B2, C2, and N2.
Yeah.
So do you see what that looks like?
Yeah.
Do you see that there's a sigma 2p, pi 2p, and so forth and so on. And
Yeah.
here are the drawings that they draw for it, which are similar to the ones I drew. Mine are a little bit different. And then there's this for O2 and F2. You'll notice that here, it looks like, I call this the Christmas tree. And here, this looks a little bit different. It looks more like, I don't know what you would call that, but not the Christmas tree. And so here, I'm going to show you these two diagrams.
Okay.
So the two MO diagrams that you want to remember are as follows. The Christmas tree first. And instead of drawing boxes like they've drawn here, I'm just going to draw lines for now.
Okay.
So we're going to do the Christmas tree first. And here's how you do it. 3 blind mice. 3 blind mice. See how they run. And you got the Christmas tree.
Okay.
But you see how the look of it is kind of like a Christmas tree. It's pointing at the top. It has boughs coming out, and then it's got a long trunk, right?
Yeah.
Okay. Now, when you're trying to remember these, the ones up the middles are all sigmas. So this is sigma 1s and sigma star 1s. This is sigma 2s, and this is sigma star 2s. And this is sigma 2p and sigma star 2p. So for every 2, you got a bonding and an anti-bonding. And it goes 1s, 2s, 2p, just like the order of the subshells, right?
Right.
Now, if those are all sigmas, where are the pi's?
The outer ones.
Right, so this is a pi 2p and this is a pi 2p star. And also a pi 2p and a pi 2p star. Now this is for all diatomics up to C2. Actually up to N2.
Okay.
So the other one, I don't really have a little thing for it, but it goes like this. So the 3 blind mice, right? But then here, you'll notice it does kind of this thing. And then the rest of the 4. So if we put boxes on these, they are labeled exactly the same as these over here. I'm going to do the labels kind of to the side. So this is sigma 1s, and this is sigma star 1s. What comes next?
Sigma 2s.
Right, and then after that.
Sigma star 2s.
Okay, and then after that, going up the middle.
Oh,
What's that?
I don't know.
Well, what was it over here? Going up the middle.
Oh, sigma 2p.
So it's still a sigma 2p, and what's the one at the very tip top?
Sigma star 2p.
2p. And just like over here, what are the ones out on the sides?
Pi.
Pi 2p and pi what for the one above?
Star.
Pi star, anti-bonding, right?
Yeah.
So these are the two MO diagrams that you get.
Okay.
Now, this is for all electrons. And I should say this is for O2 and F2. This one here. And this is counting all electrons. So I did not say valence electrons, I said all electrons.
Oh.
So if we wanted to do O2, you would not say 6 plus 6 is 12. For O2, how many electrons are there? Well, we look at the periodic table. We find out that oxygen has an atomic number of 8, right?
Yeah.
So how many electrons does O2 have?
16.
16. So we put them in like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see how I separated 11 and 12?
Yeah.
Because these are of equal energy, so I put 1 into each orbital first.
Same energy level.
Yep, 13, 14. And then 15, 16, right? So this is O2.
My drawing's messy.
Pardon me?
My drawing is messy.
Well, at any rate, here's some things that we can tell about O2. One of the things we can tell is that it's paramagnetic.
Yeah.
Why? It's got unpaired electrons. We can also tell that here, this sigma star 1s cancels this sigma star, this sigma 1s. This anti-bond cancels this bond. So we don't have a 1s bond.
Okay.
Do you see this 2s bond?
Yeah.
It's canceled by the sigma 2s star electrons.
Okay.
Do you see this sigma 2p bond right here? Because 2 electrons is a bond, right?
Yeah.
Is it canceled by any electrons in the sigma star 2p?
No.
No. So we've got 1 sigma bond here in O2.
Okay.
So do you see that we have here 2 pi bonds?
Yeah.
But you see that we have one, when we add these together, it's 1 anti-bond, right?
Yeah.
So when you have 2 pi bonds, but 1 canceled pi bond, how many do you have total?
Just one left.
You have 1 left. So this has 1 pi bond. And that's kind of what we expect for O2 using valence bond theory, right?
Yeah.
With valence bond theory, we have this.
Oh yeah, the double bond.
And we say, oh, you know, if there's a double bond, we know one of them's a sigma, one's a pi. This agrees with that.
Okay.
However, where this may be a little bit better than valence bond theory is that here we predict that O2 is paramagnetic, right?
Yeah.
And it is. If you look at valence bond theory, doesn't it look like every electron is paired?
Mm-hmm.
So what would you predict for the magnetism of O2 if every electron is paired?
Diamagnetic.
Diamagnetic, and it's not.
Right.
So that's why with valence bond theory, we never broached the subject of magnetism.
Mm.
Never. And the reason we didn't is because that model is not good for magnetism. We did approach how many sigma bonds does it have and how many pi bonds does it have, right?
Yeah.
It's because that model works great for that. But we never talked about magnetism. Here, all of a sudden, we're talking about magnetism. Why? Because we can see paired and unpaired electrons.
Okay.
And then there is the electron configuration of O2. But we're going to do O2 one more time. So O2 looks like this. if you draw this like 10 times, it becomes a lot easier.
Yeah. So we're just supposed to know this is how O2 is drawn.
Yeah, you should have this on your cheat card that O2 is this way, and anything less than that is this way.
Okay.
Unless you just memorize it like I do, because I've drawn it more times than I care to remember.
Okay.
I've drawn it more times than I can remember. So this is O2. And I'm going to go ahead and put my electrons in. And don't be so hasty when you're putting your electrons in that you don't put them in correctly. Now, sometimes the book actually shows you the molecular orbital diagram using only the valence electrons. So oxygen only has 12 valence electrons because it's in group 6A.
Yeah.
So here, what would the valence electrons be in this MO theory if you had to guess?
Well, everything in shell 2.
Right. So here's the cutoff. These are valence and these are core. So if you ever have to draw an MO diagram where you're only drawing the valence, you only draw the top part of this. And it's sigma 2s, sigma star 2s. And the reason that people do this sometimes is because if you take a look at these down at the bottom, they cancel automatically, don't they? So you're never going to get a sigma bond down here. So why bother even showing it? So here, you can see I've almost got this labeled. So how many electrons do I put into here?
12.
12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And do you see that from the 2s up, it's identical to the one for all of the electrons?
Yeah.
Okay, so never fall into the trap of using the wrong number of electrons for your MO diagram. If you have a valence shell MO diagram, use only valence electrons. If you have the complete MO diagram, use all the electrons.
So if the question doesn't specify valence, we assume all?
Well, I would say that if the question says draw the MO diagram, do the total and count all the electrons. Okay? Okay. Now, there's also the electron configuration.
Okay.
So looking at the total diagram, here's how it looks. There's the sigma 1s, and around every type of MO, you put parentheses. So you see that sigma 1s parentheses?
Yes.
Number of electrons, just like with electron configurations we've drawn earlier, it goes on the top as a superscript to the right. So here, what would go next? Sigma 1s star 2. And then sigma 2s 2. Sigma 2s star 2. Sigma 2p 2. And here, we don't write pi 2p2, pi 2p2. Here we write pi 2p4.
Um,
So here, you see these two?
yeah.
They match. Do you see these two?
Yeah.
They match. Do you see these two? So basically, I'm reading from the bottom and going up.
Okay. So, oh, okay. So I was just confused why we only had one sigma 2p, but it doesn't have an electron. The other one doesn't have electrons.
Ah, we do have a pi 2p star with 2 electrons. And since this guy's empty, we don't write it.
Yeah, that's what I was thrown off by.
Okay, so now what would we do for this electron configuration on the right? And the answer is for this one on the right, we would have to subtract these 4 electrons. So basically, this would be, let me think about this now. I don't remember actually writing electron configurations for this, but we're going to just say, you would write this essentially for this part to the right.
I mean, that would make sense.
Yeah. But you cannot write helium and then all of this because it's not helium. It's really what 2 heliums bonded together would look like.
Okay. So
And
there's
in
no,
fact, if you look at just this right here, this is what 2 heliums bonded together would look like. Because one helium has 2 electrons, the other helium has 2 electrons, that's 4 total, right?
yeah,
So here, if we look at just this part here for helium, how many sigma bonds does it have?
4.
No. That's a sigma bond, right?
Mm-hmm.
What is that one?
That's a sigma bond.
But what about the star?
And then makes an antibond.
Antibond. What do antibonds do to regular bonds?
Cancel them.
Okay, so here's a sigma bond, and here are 2 electrons that fully cancels that sigma bond. So how many sigma bonds does helium have? He2.
So just
I can see I'm confusing you. So here's what I'm going to do.
So just okay. Just
So here's helium with its 1s, right?
yeah.
And here's helium with its 1s. Here's the sigma 1s. And here's the sigma star 1s. So can you see here that this is a sigma bond? And this cancels a sigma bond,
Okay.
right?
Yeah.
So how many bonds does He2 have? Has no bonds.
Okay.
So this says that
They don't
helium
bond.
does not bond to helium. That's what this says.
Yeah.
So does helium bond to helium as far as we know?
No.
No, it doesn't. So this fits right in line with that. And so you might look at this and first say, well, why would we do this if they don't bond together? And the answer is because it shows that they shouldn't bond together. And if we look at this diagram, so you can tell that I'm going to be doing one that's either oxygen or fluorine. I'm not going to draw the boxes anymore. It's too much trouble. Okay, let's do Ne2. How many electrons in Ne? It's okay to look at a periodic table.
Ne. Oh, 20.
20. So, okay, that wasn't the answer I was expecting. Ne has 10, and so Ne2 has 20, right?
That's what you
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So do you see how these two cancel?
Yeah.
Because they're both 1S's, right? Do you see how these two cancel?
Yes.
Do you see how these two cancel?
Mhm.
2p, 2p?
Yeah.
Sigma 2p, sigma 2p. Do you see how these two cancel? Pi, pi, 2p?
Yeah.
These two cancel, right?
Right.
So how many sigma bonds does Ne2 have?
0.
0. How many pi bonds does Ne2 have?
0.
0. So how many bonds total does Ne2 have?
0.
0. So does Ne bond to Ne?
No.
No. And is that what we expect for neon?
Yeah.
Okay. So showing that there are no bonds is useful. It confirms the behavior we know is that we know to expect from neon and from helium. So it seems like an exercise in futility because it doesn't bond together, but it's not. It's an exercise in confirmation that it doesn't bond together.
Right.
Okay. Now there is a way to calculate the bonds. So the number of sigma bonds is equal to, basically you count all these electrons in the sigma orbitals. So 1, 2, 3, 4, 5, 6, right? If you have 6 electrons in the sigma orbitals, that would equal 3 bonds, right?
Yeah.
So the number of sigma bonds here would be 1/2 of the bonding electrons. But then the anti-bondings cancel, right?
Right.
So 2 electrons cancels 1 bond, right? So you'd have 1/2 of the anti-bonding electrons. And what do you think the formula? And of course, when we say number of sigma bonds, this formula is for sigma electrons, right?
Yeah.
Now, what would you have for the formula for the number of pi bonds? It'd be 1/2 of the pi bonding electrons minus 1/2 of the pi anti-bonding electrons. This is redundant when I put star here and AB here, but I'm going to do it.
Okay.
And what if you just want to look for the total number of bonds? It's going to be 1/2 of the bonding electrons minus 1/2 of the anti-bonding electrons. So you could do that for all of them and get the total bond count. Are you with me?
Yeah.
Now, I think the book may actually give this formula as 1/2, something like this, where they take the 1/2 on the outside. But you see how these two formulas are the same?
Yeah.
So that's another way to do it. like to start off the way I did, where I show that these cancel these. And the
Yeah.
reason they cancel is if we go back to a 1s, oops, a 1s, and a sigma 1s, and a sigma star 1s, do you see how this distance here is smaller and this is greater?
Yeah.
So the idea is that the electrons in the antibonding orbital are so unstable that they completely cancel the ones in the bonding orbital.
Right.
That these are more unstable than these are stable.
Okay.
Okay. And to really exaggerate it, you could do something like this. So that's the stability, and there's the instability. So these guys totally cancel that. Okay. All right. That's MO theory. Not much to it once you go through all of it. What do you want to do? You want to do some problems with MO theory, or do you just want to do some problems from the back of the book and see what you know?
Or what I don't know.
Okay,
Yeah.
let's find out what you know and what you don't know. So here are some problems from the back of the book. Number 2. Draw the Lewis structure for NF3. So nitrogen has 5 electrons. Fluorine has 7, but there's 3 of them, so that's 26 electrons. So I'm going to draw nitrogen in the middle because it likes to make 3 bonds and fluorine only makes 1. When I give the fluorines an octet, I've used 24 electrons. I'm going to put 2 more on nitrogen, and there's your Lewis structure. So it asked for the electron pair geometry. It didn't ask us to draw it. It just asked us what's the electron pair geometry. Well, I'm going to say that it is tetrahedral. What's the molecular geometry? Since 1 lone pair and 3 bonds, that makes it trigonal pyramidal. What is the hybridization of the nitrogen atom? Well, since it has 4 pairs, it's going to be sp3 hybridized. And the reason for that is that with 4 pairs, you have to hybridize 4 orbitals, 1 s orbital and 3 p's. What orbitals on nitrogen and fluorine overlap to form bonds between these elements? Well, you could take the tact you know that on nitrogen, it's going to be an sp3 because it's sp3 hybridized. Now for fluorine, you could do the same thing. You could say fluorine has 4 pair and it's sp3 hybridized. So what's overlapping from fluorine? sp3. So that's one take on the overlap. However, do we have to have that for fluorine? And the answer is no. For fluorine, we could have a 1s, a 2s, and a 2p that looks like this. And you've got 1 orbital here with 1 electron in it, right?
Yeah.
What type of orbital is that?
Just an SP.
It's a 2p, right?
Oh, yeah.
So here, it could be a 2p orbital that overlaps some fluorine. This is the more commonly thought way of doing it because you don't hybridize orbitals if you don't have to.
So, okay.
So that's a 2p, and the orbital overlap is between an sp3 hybrid and a 2p that is not hybridized.
So either way is right?
I prefer this way. Better. Do not hybridize if not needed. So that's the answer I prefer. And ultimately, that's what matters when I'm going to be grading it. Okay. Draw the Lewis structure for 1,1-dimethylhydrazine. And here they give us a little bit of a hint at what it looks like.
Yeah.
So CH3, we already have an idea, looks like this. And what does it mean when we say CH3-2?
There's two of those.
Right, and it turns out that they're both bonded to the nitrogen.
How do you know that?
Well, because if you bond them to each other, then it can't be bonded to the rest of the molecule, could it?
No, because it is surrounded by hydrogen, I guess.
Yeah, you would have this, and then it's not one molecule, it's going to be two molecules, right?
Yeah.
So you can't do that, so that doesn't make sense.
Okay.
So do you see how this says NH2 on the back end here?
Yeah.
We know that those two hydrogens are probably bonded to nitrogen, right?
Yeah.
And the same nitrogen, right?
Yeah.
So what would you write if the same big portion is going to be bonded to the same nitrogen? You do the same thing, CH3, 2. So that 2 following the CH3 is just like that 2 following the hydrogen saying, hey, both of these are bonded to the same thing.
Okay.
Okay, now, of course, the nitrogens are going to have lone pairs. That's what we expect, right?
Yeah.
And just to make sure, we're going to count how many electrons we have here and count how many electrons we should have here and make sure that they jive, that they are correct, okay?
Mm-hmm.
So for carbon, we have 4 electrons, right?
Yeah.
And for hydrogen, we have 3 for 7 total in there.
Yeah.
Well, because there's 2 of these, we're going to say 14 electrons there.
Mm-hmm.
Plus 5, plus 5, plus 2, which looks like 26 electrons to me. Fair enough?
Yeah.
Let's count these. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we're good.
Okay.
Okay, this is used in rocket fuel. So what's the hybridization of each nitrogen?
So they're tetrahedral, so sp3.
sp3.
Right.
What orbitals overlap to form the bond between the two nitrogens?
Well, sp3.
sp3s.
Right.
Okay,
Okay.
that was easy. Draw the Lewis structure for acetamide. So here again, we're going to say, okay, CH3, right? And that's going to be bonded to this carbon. Now, Can we make this work?
Well, carbon needs 4 bonds.
Right. And if we count up electrons here, we've got 7 for the CH3, 4 for the carbon, 6 for the oxygen, and 7 for the NH2 because you got 5 plus 2.
Uh-huh.
So that is 24 electrons, right?
Right.
And here we've used 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And I'm going to take these and make a bond there so that, and this just does not look right because carbon's got 4 bonds and oxygen's got 3. I'm not feeling it, right?
Yeah.
So is there another way to do this? And the answer is yeah. What if we put the oxygen like this? Let's see how this one works out. So 1, 2, 3, 4, 5, 6, 7, 8. And if we count these up, this is 8 here, 8 here, and oops,
But carbon still doesn't have 4
8
bonds.
there for 24. So that's good, right? But we're going to take this and make a double bond, and that's looking good because everything's got an octet and the number of bonds it likes, right?
Yeah.
So this is one of those things that you should put into your little tool chest. When you see this CO in a molecule, it's probably C double bond O.
Okay.
Okay. So what are the electron pair geometry and molecular geometry around the 2 carbon atoms? So here, what's the EPG?
Tetrahedral.
And what's the MG, molecular geometry?
Tetrahedral.
And what are the angles?
1095.
Okay, how about this carbon? What's the EPG?
Trigonal planar.
Trigonal planar.
Yeah.
What's the MG?
Trigonal planar.
What are the angles?
120.
120.
Okay.
Okay, what is the hybridization of each of the carbon atoms? So this guy, what's the hybridization?
sp3.
And how about this guy?
sp2.
sp2. What orbitals are overlapping?
sp3 and sp2.
That's right.
Okay.
Okay, that's between each of the oh, it didn't ask for the carbons, it asked for the carbon oxygen. Oh. So what's overlapping here? Well, for this, we need to know the hybridization of the oxygen. What's the hybridization of the oxygen?
Oh, sp2.
Okay, so what's overlapping here to make those bonds?
sp2 and sp2. I think.
Okay, that's only one of the bonds. What about the other one?
Again, the same thing?
No. Remember, this is valence bond theory. So you have a double bond. One bond is a sigma bond. That's that one. What's the other one?
Oh, the pi bond.
How do you make pi bonds?
Well, they're on the outside. I don't know what you're asking.
Well, what type of orbitals overlap to make a pi bond?
Oh, p. Oh, the leftover piece.
Right, the leftover p.
Yeah. Okay.
The leftover p orbitals make the pi bond.
Right.
So this is the sigma bond, this is the pi bond. So do you understand that question now between carbon and oxygen? what orbitals overlap to form the sigma and pi bonds? The sigma are the sp2 and sp2. The pi are the unused p's, which are actually used. So we should call them the unhybridized p.
Yeah. Okay.
Okay, specify the electron pair and molecular geometry for each of the underlying atoms. In the following list, describe the orbital set used by this atom in each molecule or ion. So we need to give the, for each of these, the electron pair geometry, the molecular geometry, and the hybridization. Okay.
Okay.
So that means we need to start off with what? Not the formula, but
Lewis.
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 So how many electrons does selenium have?
6.
6?
Yep.
Okay, so we're looking at what? 12 plus 4 is how many electrons?
16.
16. So I can see the writing on the wall. It's going to look like this.
So we got linear.
Does that make sense?
Oh, yeah.
So what's the EPG?
Linear.
What's the MG?
Linear.
And what are the angles?
180.
What's the hybridization?
SP.
Good. How about SO2? SO2 is going to have 18 electrons, so I can already see the writing on the wall. That's only 16, so the other two go here.
So it's bent.
So what's the linear electron pair geometry?
Oh, trigonal planar.
Good.
Bent.
And what are the angles?
120.
120. Hybridization.
SP2.
Correct. Okay, CHO.
It's CH2. Oh.
What? CH2O. Sorry about that. So you're going to put carbon in the middle, and I can already see the writing on the wall.
Okay. Oh, okay.
Because we're going to need what? 12 electrons?
Yeah.
And you're going to end up not having 2 on carbon, so you have to make that double bond to get the 12 to give you octets everywhere. Okay, so the carbon atom is what they have underlined. What's the electron pair geometry?
Trigonal planar.
What's the molecular geometry?
Trigonal planar.
What are the angles?
120.
Hybridization?
SP2.
Okay. NH4 plus is going to have 9 electrons, but the plus sign does what to that number of 9 electrons?
Makes it 8.
Makes it 8. Because to get a positive charge, you have to take away an electron. Now, when we draw the Lewis, what do we have to do to this guy that we haven't done for any of the others?
To draw the molecular.
I would say the bracket.
Oh, yeah.
Okay, EPG.
Tetrahedral.
Excellent. MG.
Tetrahedral.
Angles.
1095. SP3.
SP3. Okay. Pretty easy, right?
Yeah. The drawing part is more difficult.
Well, it didn't ask us to draw.
I mean,
Okay,
General.
number 10. What is the orbital set used by each of the underlined atoms? So A, what's the set used by nitrogen?
sp3.
Say that again.
sp3.
Yes. How about the carbon?
sp2.
Okay. For B, the first carbon.
sp3.
Yes. The second carbon.
sp2.
The third carbon.
sp2.
For C, the first carbon.
sp2.
The third carbon, but the second one that's been underlined.
sp.
Okay. So there is a reason why we don't need to spend a whole lot of time on some of the things in this chapter, is because once you get going, it's not hard at all. Draw the Lewis structure of the acid HSO3F and its anion SO3F minus. So here we're probably going to do this. And start with the anion.
Oh, okay.
How many electrons with the SO3F minus? Well, 6 for sulfur, 18 for oxygen, 7 for fluorine, and 1 more for the charge, right?
Yeah.
And that's going to be 25, 32 electrons, right?
Yeah.
So that ends up being 32 electrons right there. Now, we're not too happy with this Lewis structure because this is a +2, -1, -1, -1 for a total of -1.
Okay.
So wouldn't this be better? Where the formal charges are 0, 0, 0, 0, and -1.
Yeah.
Okay, so where am I going to put the hydrogen onto this? And how many electrons should I have for HSO3F? Well, for HSO3F, we're going to have 1 + 6 + 18 + 7, which turns out to be 32. Now, what did we say about these types of ions that have oxygen in them and they're acids? What atom does the hydrogen bond to?
Oxygen.
Oxygen. So doesn't it make sense to do this? So since this already has 32 electrons, I'm just going to make one of these lone pairs into a bond to hydrogen. Why did I bond the hydrogen to that oxygen and not the others?
Because the others have double bonds.
The others already have 2 bonds. And in addition, doesn't that oxygen have a -1 formal charge? And wouldn't it be attracted to an H plus to make a bond?
Yeah. Now it's
And how do we know this is an H plus and not an H? Well, because if it were an H, it'd have an electron and we'd have 33 electrons. So this is it. Okay. What's the molecular geometry and hybridization for the sulfur atom in each species? And notice they tell us oxygen is bonded to hydrogen. So what's the hybridization for that sulfur?
sp3.
sp what?
3.
Okay. And how about here?
Well, it's the same.
Yep. So the hybridization doesn't change because the reaction occurs outside of that atom, away from the atom, not on the atom. Okay.
Okay. I believe you.
Okay. What is the hybridization of the carbon atoms in benzene? C6H6. So C6H6 looks like this.
Yeah, that's a fun one, huh?
It's real easy to draw. And then the double bonds, you just alternate them. Doesn't matter which two carbons you start on, just alternate them.
Okay.
So what's the hybridization of each carbon?
SP. Oh, SP2.
sp2. So that means that each carbon looks like this. With the unhybridized P coming straight out of the middle of the carbon, right?
Yeah.
Okay, what's bonded to here? A hydrogen. Now, what are you bonded to here? Another carbon. How about here? Another carbon. And so what I've drawn is basically this part of the molecule right here, but I haven't drawn the hydrogens and everything else. Now I'm going to stop for a minute there. And I'm going to draw this a little bit differently. Okay, you're going to see why I did this in just a moment. So what's the hybridization of, see this carbon that I'm pointing to here? That's this one. What's the hybridization?
SP2.
So really I should have another sp2 here and sp2 here, right? But there's a P on this one, isn't there?
Yeah.
And there's a P on this one?
Yeah.
Now this guy is bonded to that guy. And this guy is bonded to this guy. And there's a P here and a P here. And then both of these guys are bonded to this guy and there's a P here.
Yeah.
So what I'm trying to show you is that there are 1, 2, 3, 4, 5, 6 p orbitals all in the same circle, all in the same direction, right? So guess what the electrons do? They don't stay just between 2 p orbitals. They spread out between all 6 of them.
Yeah.
So there are, in this donut on top of these carbon atoms and this donut on the bottom of the carbon atoms, there are 6 electrons spread out. Now, what do you think is going to be better? Keeping 2 electrons directly between 2 carbon atoms in 2 p orbitals, or taking those 6 electrons and allowing them to spread out along both donuts above and below?
Spread out.
Spread out, and that's what they do. Now, when they spread out like that, isn't that going to make this molecule kind of really stable?
Yeah.
And it is. It's really stable. So here, describe the sigma and pi bonding in this compound. You would say that each carbon bonds to 2 other carbons through sp2 sigma bonds, right?
Yeah.
And then all 6 carbons overlap these 6 p orbitals to delocalize. So delocalize is the word used to spread out, delocalize. to delocalize the 6 pi electrons. And your book has a great drawing of this that I can't do. This is the closest I can come. But here's what your book does. You see the donut above and below?
Yeah.
That's the overlap of the top of the p orbitals and the bottom of the p orbitals. And you see this? This is each one being sp3 hybridized, bonding to a hydrogen atom. For me, I only drew one of them. I didn't draw all of them.
Yeah.
And you see that they took this guy and they rotated it like this. So you're looking at it from the side now in this drawing here.
Yeah.
So if you can imagine, I'm going to draw in my book, if we had a double bond here and put the 2 electrons here and put the 2 electrons here and 2 electrons here, can you see how much space we're not using for those electrons?
Yeah.
Now, if we say, you know what, we're not going to constrain them to between 2 carbons and let them spread out, can you see how much more space you get to use?
Mm-hmm.
And it's all about spreading those electrons out because they repel one another. So here, this molecule is extremely stable. I mean, it does combust. I'm not saying you can't make it chemically react, but we'll learn in some cases, like in chapter 23, a double bond will react where this one will not react.
Okay.
So that means a double bond is more stable, or I should say is more reactive than this. So this, in fact, is not 3 double bonds in there. It's not. So here, it's not 3 double bonds in there. The electrons are spread out. And you see this circle right here? That's kind of a way to say that, hey, those electrons are spread out and they're not constrained to these double bonds.
Okay.
So this is one of the molecules where you can actually draw the resonance hybrid instead of say, hey, it's an average of these 2. Okay. So that's number 14. Number 16. What is the electron pair and molecular geometry around the central atom in sulfuryl chloride, SO2, Cl2? So we're going to do this. To start with, right?
Yeah.
How many electrons? Well, sulfur is 6, oxygen is 6, but there's 2, so that's 12. Chlorine is 7, there's 2, that's 14. Now, when we add these together, the smart thing to do is 6 and 14 is 20, right?
32.
32. I would not add these up in order because it's not as easy.
As long as you get the right answer.
But you also want to do it the easier way so that you're more confident that you're right. 6 plus 14 is 20 all day long. I can do that all day long. 20 plus 12, 32 all day long. 6 plus 12 is 18. I can do that. 18 plus 14, I have to think about is 32, right?
Yeah.
So math trick 101. Conquer your problem by making it into smaller, easier problems.
Work smarter, not harder.
Yeah. Okay, is this 32?
Yeah.
Now here's how I count. 8, 16, 24, 32. Count by 8s. Okay, now this is not very good because sulfur has a +2 formal charge. So you can see the writing on the wall.
We're gonna double bond.
Okay, so what's the EPG?
Tetrahedral,
Tetrahedral. And the angles?
1095.
And what's the MG?
Tetrahedral,
What are the angles?
1095.
Yep, 109.5. What is the hybridization?
SP3,
SP3. And because it's SP3, what would we expect the geometry to be?
what do you mean?
Well, you can get geometries from hybridization. What do we expect the hybridization to result in? What geometry?
Tetrahedral.
Tetrahedral still. Okay. For each compound, decide whether cis and trans isomers are possible. So let's review from yesterday, cis versus trans. So for cis versus trans, you need your carbon-carbon double bond. You need 2 hydrogens bonded to the carbon-carbon double bond and 1 hydrogen bonded to each carbon of the carbon-carbon double bond, right?
Yeah.
Not 1 hydrogen or both hydrogens to 1 carbon, 1 apiece.
Okay.
And then if the hydrogens are on the same side, and I'm going to put this in quotes, it's cis. And if the hydrogens are on opposite sides, it's trans, right?
Yeah.
And here is what we mean by same side. That's cis. And that's trans. Okay, so we've done our review. So does A check off everything on the list?
Well, it's tricky.
Carbon-carbon double bond?
Yeah.
Yep. 2 hydrogens?
Yeah.
Yep. 1 hydrogen bonded to each carbon?
Yes.
Yep. Are they on the same side or opposite sides?
Opposite.
Trans.
So we don't. Okay. Never mind.
Okay. Now it says, if isomerism is possible, draw the other isomer. Is isomerism possible? And the answer is absolutely. So let's draw the other one.
We would just flip it, rotate, mirror image it, kind of.
Mirror image one side.
Yeah.
So you see what I did is I flipped these two. So it's trans, and then I just drew cis.
So you can do that.
Well, it said, if it's possible, draw it.
So it's asking you if it can be either or, draw the other.
They're asking you, if it is trans, draw the other. If it is cis, draw the other.
Okay.
But if it's neither, don't bother.
Okay.
Okay, how about this one? Cis or trans?
It could be both.
Nope.
No.
How many hydrogens do you need bonded to the carbon-carbon?
2.
1, 2, 3. Game over.
So it is a 1-to-1 ratio.
It's not about 1-to-1 ratio. You need 2 hydrogens, 1 for each carbon, and they have to be on separate carbons.
Okay.
So it's not really about trying to get a 1-to-1 ratio. It's just understanding that this is neither cis nor trans. Because if you look at those two, you're going to say, hey, it's trans, right?
Mm-hmm.
But if you look at those two, you're going to say it's cis.
Mm-hmm.
So if there's no clear cis or trans, then it is not cis or trans. But if we look at the one above, do you see those two hydrogens are opposite? It's clearly trans.
Yeah.
There's no way you could call this cis. So cis and trans can only be applied where it is obviously a cis or a trans.
Okay.
So do you see this one? The two hydrogens are on the same side.
Right.
That's cis, no ifs, ands, or buts. Okay, so you see why you need two hydrogens and not three?
Yeah.
Okay. Now, C, it's cis. So let's draw the trans. What are you going to do?
You're gonna switch two of them on one side.
Yep. Doesn't matter which side. The answer is absolutely not.
Right.
So there you go. And this one is the trans. Okay. So there are some nitpicky details you need to remember for cis and trans. And the nitpicky detail is two hydrogens, one on each carbon.
Right.
Then you're okay. How many hydrogens?
Two hydrogens,
On what?
one on each carbon,
Which carbons?
the double bonded carbons.
There you go.
Okay.
And so you can see that right here. You need two hydrogens bonded to carbon-carbon. It's got to be the double bond. Because guess what? See that? How many hydrogens bonded to those carbons?
One of each.
Two, right? And is one carbon bonded to, is one hydrogen bonded to each carbon?
Yeah.
Is this cis or trans?
Cis.
It's neither cis nor trans. There's no double bond.
Right.
So the deal with the carbon-carbon double bond is, what do we know about rotation about a double bond? Is this possible?
No.
No. How about rotation around a single bond? Is that possible? Absolutely.
Yeah.
So single bonds rotate, which means this guy can do this all day long. And in fact, this molecule, unless it's 0 degrees Celsius or 0 degrees K, this molecule is spinning like a top.
What is that?
It's a chlorofluorocarbon. It's something you might use in a refrigerator. So it spins like a top. Now, if there's a double bond, it wouldn't spin like a top. Okay, so that's the answer to 16. Oh, 18. Okay, here, this is some MO stuff.
Okay.
And this is interesting because we're looking at lithium ion plus ion and lithium minus ion, right?
Yeah.
So we know that for anything below oxygen, we use the Christmas tree, right?
Yeah.
So Christmas tree, 3 blind mice, 3 blind mice, see how they run. Bet you didn't know that that nursery rhyme was invented so people could remember the MO diagram. And if you believe that one, you are gullible. So it's my hope that you didn't believe that. Okay, so let's look at lithium plus. How many electrons does lithium have?
Total? 3,
Okay, how many does two lithiums have?
6,
So how many does two lithiums with a +1 charge have?
5.
Okay, so we're looking at 5 electrons. Where are we going to put them?
In the 1s.
Not all 5 of them, right?
Right. So from least to most, or most stable to least.
Okay, so 1s, 2 of them there, then where?
Sigma star 1s,
Okay, and then where?
sigma 2s.
Okay, so let's look at bond order. So first we're going to look at sigma bonds. So sigma bonds is going to be 1/2 of the bonding electrons in the sigma bonds minus the anti-bonding electrons in the sigma bonds. So how many bonding electrons do we have?
Well, I want to say just 1.
1, 2, 3.
Oh yeah. I mean, for the end.
How many anti-bonding electrons do we have?
2.
2. So this is half a bond.
Yeah.
Now, does that make sense? Do these two cancel these two?
Mm-hmm.
Absolutely. And then when you have 1 electron, is that a full bond?
No,
You need 2 electrons for a full bond. So how much of a bond is this?
a half.
Half a bond. So let's look at lithium -1. How many electrons here?
7.
7. So now let's put the rest here. We've got 1, 2, 3, 4, 5, 6, 7.
Right.
So bond order, how many sigma bonds do we have? So 1/2 of the sigma bonding electrons minus the sigma star anti-bonding electrons, right? How many bonding electrons?
Well, we have 3 full sigma bonds.
How many bonding electrons?
6.
1, 2, 3, 4.
1. Okay. Oh,
This is a bonding orbital.
I'm
This is anti-bonding.
yeah.
This is anti-bonding. And this is bonding. So basically, anti-bondings have a star, bonding don't. So how many bonding electrons?
4.
Good. How many anti-bonding electrons?
3.
Okay, 4 minus 3 is 1. 1 times 1/2 is 1/2. So these both have a bond order of 1/2.
Right.
So it's clear to me that you need to just kind of get used to the terminology of bonding and anti-bonding.
Mm-hmm. And pay attention to the star.
Yeah. Platinum hexafluoride is an extremely strong oxidizing agent. It can even oxidize oxygen, which is saying something. Its reaction with O2 giving O2 plus PTF6 minus. Sketch the molecular orbital energy diagram for O2 plus ion. Okay, so for O2, we're not going to use the Christmas tree. We're going to use the palm tree. I'm going to call it the palm tree because palm trees are round at the top, right?
Yeah.
And this guy is kind of round at the top. That's kind of round, right?
Yeah.
Now, if we want to do the manufacturing way of filling this out, Here's how it goes. Sigma, 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 sigma. Anything up the middle is a sigma.
Yeah.
Next thing, these are pi's on the outside, right?
Yeah.
Okay, now for every 2 sigmas, the bottom one is a bonding. The one above it is what?
Anti-bonding.
Okay, so I'm going to fill in the anti-bondings. Oops, made a mistake. And the same for the pi's. The lower one is the okay one, the bonding. The upper one is the anti-bonding.
Okay.
Okay, and then what do I put in for letters? 1s, 2s, 2p. And the pi's are always 2p's, aren't they?
Yes.
Okay, how many electrons in O2 plus 1? 8 plus 8.
Is it 15?
8 plus 8 is 16, right?
Yeah.
And what about the charge?
So -1, so 15.
So 15 because of the charge. So that's 10, 11, 12, 13, 14, 15. Okay, now they ask you, sketch the molecular orbital diagram. How many net sigma bonds and how many net pi bonds? And what is the oxygen-oxygen bond order? And how has it changed when you take away an electron? So here, we're going to do net sigma bonds is equal to 1/2 of the sigma bonding electrons minus sigma star anti-bonding electrons.
Okay.
So how many sigma bonding electrons? 2, 4, 6. Agreed?
Yeah.
How many sigma anti-bonding electrons?
4.
4. So that means we have a net 1 sigma bond.
Okay.
Now let's look at net pi bonds. Net pi bonds are going to be 1/2 of the pi bonding electrons minus the pi star anti-bonding electrons. Okay, how many pi bonding electrons?
Just 1.
Where do we find the pi electrons?
The outer part.
Okay, are these bonding electrons or anti-bonding electrons?
Bonding.
So how many there?
2.
How many there?
2.
So how many pi bonding electrons?
4.
Excellent. How many pi star anti-bonding electrons?
Just 1.
Just 1. So 4 minus 1 is 3. So you got a 3/2 bond order. So what is your, notice here they ask, what is the oxygen-oxygen bond order?
What does that mean?
So the overall bond order is going to be 1 plus 3/2, which I'm going to say is 2.5. Because 3/2 is 1.5.
Yeah.
So that's your overall, that's your bond order. So net is different than overall, right?
So for overall, we first get the net and then add them up.
Yep. And sometimes your net number of pi bonds is 0.
Yeah.
Like here, we didn't even look at pi bonds because there were no pi electrons, were there?
Right.
So technically, what is your net number of pi bonds when there's no pi's?
0.
0. And we don't like to talk about zeros because they're boring. Okay, now it further asks, well, what about O2?
just regular O2, neutral.
So what would we do for net sigma bonds? How would that change? Where would the next electron go for O2? Because that has 16 electrons. Where would it go?
It would go in that top left anti-pi bond.
Okay. So how would that affect your net number of sigma bonds?
It wouldn't.
It would not. How would it affect your net pi bonds? If we had another one there.
Well, we would do 4 minus 2, and then so half of that would be 1.
Okay, so the net would be 1 instead of 1.5, right?
Yeah,
And what would your overall be?
2.
So in answer to the question, how has the bond order changed on taking away electrons from O2 to attain O2 plus? Well, the bond order increased from 2 to 2.5.
Mm-hmm.
So here, it increased from 2 to 2.5 when we made O2 plus.
Yeah.
Is O2 plus paramagnetic?
Yeah.
And this is what makes it paramagnetic.
Yeah.
Okay?
Okay.
Well, I think that's probably a good place to kind of call it quits, especially when it says 24, please refer to the book. We're not going to do that.
Okay.
We've been at it for almost 2 hours.
All
So your
right.
children are probably wondering where mom is.
No, they're not. They're at daycare.
They're totally saying, it's almost lunchtime.
Right.
You need to feed us. I'm surprised I don't hear the pounding on the door.
All
And then
right.
there's your dog too. Your dog's got to eat.
She's fine.
Oh, he's been in the room?
Yeah.
I did not notice. He's a very good dog.
Yeah.
Okay. Well, the quiz is Monday, but we always have a Q&A on Monday too, so you can ask questions before you take the quiz.
Oh yeah. Quiz. Okay.
And I think the quiz is actually opened. It may already be open. I don't know.
I'll probably try it this weekend.
And you get to take it as many times as you want until the time runs out.
Okay.
I would suggest on this chapter, since you kind of got the late start because you were studying for the exam, that's always a problem with this particular 4th exam is people don't put as much into chapter 10. You can get away with it because you're learning how quickly it is to learn these things, right?
Yeah.
But you're also finding that the terminology is key.
Yeah.
And so focus on understanding the terminology, pi, pi star, sigma, sigma star, the parts of MO theory, that you use orbitals of the same energy. You get 2 for 2. You get 1 bonding and 1 anti-bonding, and you fill it, even though this isn't the real rule, you fill it like Hund's rule and the Pauli exclusion principle. Okay.
So what chapters are we doing? We're doing 9, 10, 11, 23?
9, 10, and 23.
Oh, okay.
And 23 is going to be a lot like your chapter 12 in Chem 2, which is organic chemistry.
Intro to, so
You have to recognize functional groups. You have to know some physical properties. You have to know isomers. You have to know naming isomers. You have to know how to what the drawings mean when we don't draw carbon atoms, things like that.
yeah.
It's going to be very similar to what you did in Chem 2.
Okay.
Okay. And some simple chemical reactions.
So it's just an intro to OChem.
I don't even think it's really an intro to OChem. It's like it's like the trailer for OChem, for intro to OChem. It's a 2-minute trailer. That's it. So that should tell you something about OChem.
Yeah.
OChem is one of the most difficult subjects students encounter in chemistry
Yeah.
until they get to PChem, and then they realize that OChem was really easy.
No, thank you.
Who knows? You know, you may get into OChem and you may love it, and you may say, you know what? I don't want to be a doctor anymore. I want to be a chemist because chemists rule. They figure stuff out. Doctors, they just learn how to do things. Chemists, they figure stuff out. That's where I want to be. Plus, chemists don't have to deal with dying people and people who won't take your advice. Well, maybe you ought to lose a few pounds and, you know, eat some more fruits and vegetables. And then they don't listen to you. Next week they come in, or 3 months down the road, they come in, doctor, I'm not getting any better. Like, well, are you eating better? No.
What kind of jobs can chemists have?
What's that?
What kind of jobs can chemists have?
You can actually have jobs in industry where you're figuring stuff out, new ways to do things, optimizing chemical reactions. Some people work in theory. A lot of people teach. A lot of chemists go into biochemistry or biology because it's easier to transfer from chemistry to biology than the other way around. Because biology is basically based on chemistry, not the other way around.
Yeah.
So chemistry just opens up all sorts of doors if you wanted to.
Yeah.
So you could work for the government if you wanted to. Lots of chemistry jobs in the government, lots in private industry. Like, you know, all those people who've been making the vaccines, you know what they are?
Are they chemists?
They're chemists.
Or biochemists?
Yeah, very specialized chemistry. And let me tell you, those people are not biologists who became chemists. They're chemists who are also doing biology.
Yeah.
So there's lots of opportunity for chemists. There always will be. There's, you know, guess who comes up with all the different products for packaging that we throw away?
For packaging?
Yeah, chemists. I mean, who invented the soda bottle? A chemist. Who invented the aluminum can for a beverage? A chemist.
Yeah.
Because it turns out that that aluminum can is not just pure aluminum. It's actually coated with a plastic on the inside that doesn't interact with your food.
Yeah.
Yeah, you didn't know that, huh?
I don't drink soda.
Do you
No,
drink
not-
beer?
No.
You just drink water.
Well, coffee, of course.
Of course. That's your vice. Coffee, huh?
Yes.
I'm gonna find out who I can blackmail you to and say she drinks coffee, not tea. She drinks coffee.
It doesn't matter.
And you're gonna go to hell or something like that. I can tell already
Oh gosh, that's not nice.
for drinking coffee.
Oh man.
That means let's see, if you drink coffee, then chocolate's okay too, isn't it?
Yeah.
Okay. Well, here's my coffee. You did a good job today. Work on the details.
All right. Will do.
All right. Have a good weekend.
Thank you.